Hey everyone, welcome back to another fun and exciting pre-calculus class. Today we are going to be wrapping up chapter number 9. We'll be in chapter 9, lesson 3, finishing up de Moivre's theorem. Probably the hardest part about this lesson is saying the guy's name. So if you speak French, maybe you can message me and let me know how to say it, but I'm trying my best, right? So go ahead and look down at your book. We're going to jump right into it because this is fairly complex. Not once you kind of get it, once you kind of get going in it, it's like, oh, okay, that's not bad. But it's the kind of getting it plugged into the formula, things like that. So jump down to your book, look at page 184, if you will, page 184. And we're going to be talking about this guy right here, good-looking fella, Mr. Abraham. Let's just call him Abe, okay? That'll be a whole lot easier than de Moivre, or however you say it, okay? So here's his theorem. Here's the concept behind his theorem, all right? We've been talking about it, what's going on. So the idea here is that he has created a formula that allows us to generate or to raise a complex number to any power. So if we want to cube it, if we want to take it to the 5th power, if we want to take it to the 12th power, doesn't matter. His formula will allow us to do that. That's what it's all about. That's why we use it. And you can see it there on table D. So if you will, look down here at example number 4. I'm going to do it on my computer. You can kind of follow along in your book. Make sure that you're writing these steps out as we're going. All right, so we have, again, example number 4. This is the question right here. They say, we want you to find that to the 3rd power. So we want to find that complex number to the 3rd power. How are we going to accomplish this? Well, we're going to use this theorem. So we're going to plug, basically, here's the format that we have right now. That's this format right here, okay? So we're going to plug this into that formula, and then we're going to solve the formula. So let's just go ahead and do it. Let's talk about what we're looking at. Remember this R, that is your hypotenuse. Here is your theta. Here is your, and your theta is on your, well, this one right here in the complex number would be on your x-axis, right? And this is your theta on your y-axis going up. So remember the theta is the angle. That is the imaginary. That tells us which line that we're on. We're on the imaginary axis, which is the y going up and down. And then here is where we would find our exponent. Remember when we did these in Algebra 2, like solving for the nth power of something? N is just the unknown power, okay? So in this case, our n is going to equal 3, our r is going to equal 4, there's imaginary right there, and our theta is going to be 300. So what we want to do now is just plug those things into this formula and make it happen. All right, so let's go ahead, and our r is 4, so we're going to start with 4. Our n is going to be 3, so we'll put 3 here, and then we'll have a bracket, and then we're going to write the cosine of n theta. All right, what is n theta? Well, there's our n right there, so we're going to say 3 times theta. Well, what's our theta? In this case, our theta is 300. So times 300, right? And then we are going to do plus imaginary sine of n theta. So n, again, is 3, and our theta is 300. And then we'll put a parenthesis and a closing bracket. All right, so now we just want to start solving what we can solve, do what we can do here. 4 to the 3rd power is going to be 64. That's 4 times 4 times 4. We can just solve this right here. So that's going to be the cosine of 900 plus the imaginary sine of, again, 900. All right, and now this is where your book kind of goes in a different direction than what you could do, because you have calculators that can solve this right here, right? Most of you do. So I have a calculator that can solve this. So if I come out here, bring out in my calculator, I can do the cosine of 900. It will actually solve that out. So I'm going to show you two ways. So the cosine of 900 equals -1. Okay, so I could just do it right there. Or I can also do it this way. So I could do, remember, it's almost like we're in a circle, right? So we have to wind our circle backwards because we're at 900 degrees. There's not 900 degrees in a circle. What we're technically in is we're in our third revolution around the circle. So if you wind it backwards once, that's 360. Wind it backwards again, that's 720. And then that puts us in, so subtract 720 from this, and you are going to get 180 degrees. So this is inside of our unit circle. 900 is not inside of the unit circle. So you can do it either way there, and then you could do the same thing here. I sine of 180, because you're going to get the same thing there. And so 64 times, and this is cosine right there, okay? So you can do it either way, and then from your calculator from there, then you can plug that in if you want, and we just did it. So we got 64 times cosine of 180 or cosine of 900. Either one of those is going to give you -1, and then you're going to have plus the I sine of 180. And if you go back to your calculator, or maybe you know this from the unit circle, either one, so you do the sine of 180 equals 0. Let me show you that it's the same thing. The sine of 900 is going to be the same. They're both 0 because they're in the unit circle. You wrap it 3 times and you come up with the same thing. So 0. So I times 0 basically. So what happens here is really this guy just goes away. So you end up with 64 times -1, and so you get -64 would be your answer. And it might sound weird. That might be like a really weird answer for you, right? I mean, because we're going back here and we're like, okay, what did we even solve? And you're not always going to get that. Sometimes you'll get different things, okay? Sometimes the I doesn't cancel. You don't get a 0 for every I, right? So sometimes there's going to be more involved there. But what we did was we found that right there, that trigonometric number, that trigonometric coordinate, we found that to the third power, okay? And the way that we did that was we used de Moivre's theorem, plugged it in, worked it out, and it gave us -64. You just write down whatever it gives you. Whatever your answer is, that's what you're going to put, okay? Jump back here to the book. Turn the page over to 185. De Moivre's theorem may also be used to find roots of a complex number. To do this, write the root as a fractional exponent. Study example 5 for the procedure, and that will be used on all of those. I'm going to go ahead and solve this as well, but let me talk about what's going on here. This example number 5, I'm going to try to make it fast. I hope this video is not like 45 minutes, but this is kind of heavy right here, okay? So I feel like that last example, you're like, okay, I just plug in and just solve it. It's not too bad. This one's a little bit different. So let me talk about this before we start solving it. Example number 5. Find the 3 cube roots of 8. And right now you're going, what are you talking about? There are not 3 cube roots of 8. And I know, I mean, yes, I understand that, but I want to, let me show you something real quick here. Let me kind of transition back over here. And when I say the 3 cube roots of 8, so let's think about this. Let's think about what does that mean? Well, we know that 2 times 2 times 2 equals 8, right? So up until this point, that is the only cube root that we've done. But there are more cube roots. You might say, no, because -2 times -2 times -2 actually gives me -8. And you're right, -2 doesn't work. It's not a cube root. However, there are other things that can give you 8, believe it or not. Imaginary things, okay, possibly. Because here, what we really have in a way, think about this, is we have 8 plus imaginary 0. Because what happened earlier when we had 0 imaginary? Do you remember that? Actually, that should be 0 imaginary. I wrote that backwards, okay? Looks like oi. But we will, what we did just a second ago is when we got that imaginary 0, we just canceled it out. We said we don't even need to write it. But what we're doing here is it's almost like, hey, we're saying this is a complex number. Yeah, it's not, but it is, because we could write this plus 0 right there. So we could kind of turn this into an imaginary number. And if we do that, I mean, the theory behind that is that we have to find the multiple roots of that 8. And we can do that by plugging it into this formula and making it work out like that. Okay, so let's go through this. Hopefully this makes a little bit of sense to you. So you should know that 2 is going to be one of the answers, okay? Because that's the obvious answer. And I'll show you that using this formula, that using this method is going to yield 2. It's going to give us 2 as one of the answers, but we already know that one just from knowing what we know about cube roots and things like that. So here's what we want to do. We kind of want to follow the steps that we did there, but a little bit not different. We're going to turn this into an exponent because we need an exponent, right? We need the n. What does n equal? What does r equal? Things like that. So let's do that. Let's turn this into an exponent. So we get 8, and remember, so the 8 has a 1 exponent. So we're getting rid of the cube root and making this a fraction. So we're going to make it 1/3. 8 to the 1/3 is the same as the cube root of 8. Hopefully you remember that from algebra class. Now, what we want to do here is we want to plug this into our theorem. All right, so what is the r? The 8 is going to be the r. Your base is going to be the r, so we're going to have 8 times the cosine of, we don't have a theta. There's no theta. So we'll put the cosine of 0 degrees plus the imaginary sine of 0 degrees. Now, here's where it goes a little bit wonky in, put that there and then the 1/3. Here's where it goes a little bit of wonky in trigonometry. Because right now you're thinking, oh, this equals 0 and this equals 0. Really? Have you plugged that into a calculator lately? And this is where it's a little tricky when we get into the imaginary side of things, because if we plug that into a calculator, what is the cosine of 0? It indeed does not equal 0. It equals 1. Okay? And what is the sine of 0? The sine of 0 is 0. So you can see there we get 1 and then we get a 0. So this is going to be a little bit weird. What's going to happen with this? Well, what's going to happen with this is we're going to get multiple answers out of this. So, again, kind of going back, now we're going to plug this into the theorem, de Moivre's theorem. And so let's just go ahead and do it. You can look on page 185, and I'm just going to kind of go ahead and write it out. So we're going to apply this to this. So we're going to get 8 to the 1/3, okay? And then we're going to get our parenthesis cosine of, remember what we did is we put this in front of the 0. So 1/3 times 0 degrees plus I 1/3, or well, sine times 1/3 times 0. And so now we're just going to solve that. We're going to solve what we can solve. We can solve this right here, and here's where the 2 comes from, right? Because this is almost like the factored out part. The 2 comes right here. What is the 8 to the 1/3? Well, 8 to the 1/3 is 2. Okay, so there's your 2. It kind of comes outside, and that's where you get the solution of 2. And then we're going to do this one, and what happens here? Well, what happens here is we get 1/3 times 0. What is 1/3 times 0? 1/3 times 0 is 0. So the cosine of 0, and then that's plus I, and then what is basically 1/3 times 0 again? The sine of 0. And then we're just going to solve that. What is the sine of 0? We just did that. This is going to be 2 times, that gives us 1, right? And then we are going to get plus I sine of 0. We did the sine of 0, that was 0, so 0 times I, that's basically just going to cancel out, and we're just going to get 1 times 2, we're going to get 2. Okay, so there's where your 2 comes from. There's the first solution. Now, let's take a timeout right there. And so we got one solution. You might be thinking, oh, we're done. It only gives us one solution. But let's jump back to the book real quick and let's look at what else we need to do to this thing. Okay, so there's our one solution. There's our 2. Now, look what it says. Since a total of 3 roots are needed, why are 3 roots needed? Because it says to find the 3 cube roots. The question tells us to do that. So you're like, well, I only got 1. So how do we do that? Write 2 additional values equivalent to 8 cosine 0 degrees plus I sine 0 degrees by applying the coterminal angle rule. What is the coterminal angle rule? Adding 360 to it. Okay, so we're going to add 360. So we're just going to do that, and then we're going to have to do it again. So we're going to have to come up with a second one. So we're going to add 720 to both of them. So we're going to do this 2 more times. 1 with 360. That's for the second. That's going to give us the second one. And then 1 for 720, and that's going to give us the third solution. And so it wants 3 roots, so we're going to give them 3 roots based on the 3 revolutions around our circle. All right, so back here on this screen, what we're going to do is everywhere that we had a 0, we're going to plug that in with 360. We're basically just wrapping it around 1 time. So 0 degrees, wrap it around 360. So we're going to add 360 here and 360 here. You might say, well, that's not going to change anything. And you might be right, but you might be wrong. Okay? So let's go ahead and do our thing. And here's where you're going to be wrong. Here's where the kind of the trick comes in. Remember, we're doing it to the 1/3, and we're using de Moivre's theorem. So what we're going to do is we're going to do the same thing that we did before. 8 to the 1/3, and that's going to be times our cosine to the 1/3, right? Times 360. Remember, last time it gave us 0. That's where we got it zeroed out. But this is actually going to give us a number this time. Plus I sine of 1/3 times 360. So again, we can just do that. This is where it's going to give us our 2 again. See, we keep going back to the kind of like the principal root there of the of the cube of 8. So we're going to come back. This is going to give us a 2 again. Let me change the color there so you can see it. This new line. What does this give us? This gives us the cosine. What's 1/3 times 360? Well, you can just do that out. You can cancel it, right? So you're going to get a 120. So that's going to be 120 degrees plus the imaginary sine of, again, this is going to give us 120 degrees. Okay? And then we're just going to solve that. We're going to go through our 120 degrees now. And then we'll just kind of, so what is the cosine of 120 and what is the sine of 120? Well, you might remember from your unit circle what those are. You can always go to your front cover, or you can go to your calculator and you just hit cosine of 120. And that's going to give us -1/2. So that'll be 2 times -1/2 plus imaginary, and then we need the sine of 120. So we'll go back here. The sine of 120 is square root of 3 over 2. Square root of 3 over 2. All right, and now we just kind of go ahead and do that. We solve that. Since this is outside, we are going to have to go ahead and distribute that to both of those. So you're going to get 2 times 1/2. What is 2 times 1/2? 2 times 1/2 comes out to 1. In this case, it's going to be -1, right? Because we have to apply the negative sign to it. So we're going to get -1 plus, and this is where our imaginary is, and then we also have to distribute here. When we distribute here, that's going to cancel, and we're going to get the square root of 3 times I, or I square root of 3. So there is, so -1 plus, and we already distributed that too, so we're done with that. So there's going to be your second value. So your second value comes from wrapping it around to the 360 degrees. And then we would just do it one more time for the 720. I'm not going to take the time to actually show you that. We'll just go ahead here in the book. You can look at page 185, and you can see where we did it for the 720. So you would basically multiply the 1/3 times 720, and it gives you 240. And so you have cosine of 240 plus imaginary sine of 240, and then you multiply everything by 2, and it comes out and it gives you -1 minus I square root of 3. So you had a -1 plus the imaginary square root of 3 and a -1 minus the imaginary square root of 3, and you had 2. 2 is one of our answers. That was the first one that we got. Okay. So there you go. There are the 3 roots of the square root, or the cube root, excuse me, of 8. And you could do that with anything. You could do that with the 4th root of whatever number, 5th root, whatever you wanted to do, and you could just do it. Let's say you're doing a 5th root, you would have to do it 5 times because you're doing a 5th root. Notice here, table E, we're going to find the nth root, or the unknown root, using de Moivre's theorem. And really this is the same thing, but this is almost like just a little bit of a shortcut. So in other words, you're just going to do the same thing that we just did, except for you're going to plug into this kind of a shortcut, if you will, to find the unknown root. So what do I mean by unknown root? Again, what if they want the 7th root? Okay, they don't want the 3rd root. They want to know what is the 7th root. And so if you're looking for the 7th root, for example, they don't want the 1st root, 2nd root, 3rd root, 4th root. Okay, so they don't want you to find all of them. They only want the 7th root. So if they want that, then you would just plug into this formula and put it on there. And notice that this plots along the graph, right? So the answers that we got over here, they're going to plot right here. So anytime you do this, it will plot onto the onto the Cartesian plane, well, onto the imaginary plane, right? So we have the imaginary line going up here and the real line going here. So all right, well, that's all I have for you in this lesson. I know there's kind of a lot packed in there. It's pretty intense. So try some of these. Go back, look at the examples, come back here, watch the video again if you need to. The principle's the same. The numbers might change, right? But the way that you work the formula is not going to change. It's going to remain constant throughout the process. So whatever you get, okay, whatever the question gives you, plug into that formula, work the formula the way that I showed you, and you should hopefully get the right answer if you do it right. Okay? That's all I got for you. Hope you learned something. We'll see you later. Have a good one. Bye-bye.